Thank you. I'd like to thank the organizers for inviting me. Okay. So I just understood last evening that there is a very heterogeneous background. So my slides might appear, some part of the slides, at least a big part of the slides, require some basic knowledge of quantum information. But I try to add a few slides at the beginning so that it makes it more followable. But basically, I think the idea is that I'm going to give you an overview of the state of the art on the hardware. Where do we stand on the hardware side of quantum computation? And why is it hard to have a quantum computer? Why don't we have a quantum computer, reliable quantum computer yet? And then, through the whole other courses that you will have through the week, then you will dive in and go more into detail of algorithms and what we can do with a quantum computer. And so I think, if you, some of you might find parts of this first lecture not really followable, or don't be afraid. I think there's going to be a lot of these details are going to be detailed in the next lectures. Especially, I think Thomas is going to cover some of the basics of this. So, Sorry,
could you be a little bit louder?
Yes, I'll try. Maybe I have to put it somewhere closer, I don't know. Maybe. Okay, is it better? I don't know whether it's better. Yeah. It's better? Okay. As I was mentioning, I'm going to talk about the state of the art on the hardware side. And the focus is about fault tolerance. So we are talking about, I'm not going to talk about noisy intermediate scale quantum computing, and it's really how we can have a fault tolerant quantum computer and why is it hard. And I think that's actually basically this is the holy grail of quantum computing, trying to make quantum error correction work, trying to have devices which are reliable and on which we can do reliable computation. So let me start by explaining. So I come from a mathematical system theory background. So when we want to model a mathematical system, a dynamical system, well, we have to know what are the rules somehow. And when we go to the quantum world, these rules change from the classical world. And so let me just start by explaining what are the main features that make a quantum system different from a classical system. Okay, why quantum computer is different from a classical computer, and in which way it's harder to, it's more is a stronger device, it can do something more, and in which way it's harder to implement or to model. So the first feature is that, this is maybe the simplest one that you might all know, is that, instead of using Newton's laws to model the dynamic of a quantum of a system, here we would need to use Schrödinger's equation to model this dynamics. So the state of the system now is going to be a wave function, a function psi. So we show it with this notion of ket psi, but don't be afraid of this. This is just a function, this is a notation. So it's an object which lives in a Hilbert space, H. So it's a complex Hilbert space. And it satisfies this equation, the dynamics that you see on the bottom, ID over dt of psi. So is this a pointer? Up. Yes. So ID over dt of psi equals to H psi, where H is a Hermitian operator acting on this Hilbert space. Okay. And so the solution to this Schrödinger equation is given by this. So it's a linear equation, ID over dt, as you see. And the solution is given by psi of t, which is given by some unitary operator, u of t, psi 0, psi at time 0. And this u of t itself verifies this operator equation, evolution equation, id over dt of ut equals to h ut, where u at time 0 is identity on the Hilbert space. Okay, so in general, this is the first feature of a quantum system. Basically, in order to, when we have an isolated quantum system, a quantum system which does not interact with its environment, with other systems, then we basically model it by this Schrödinger equation, and its solution is given through this unitary operator u of t. And when we are speaking in the context of quantum bits and a quantum computer, this unitary is actually what we call logical gates. So implementing logical gates in a quantum computer means implementing different unitary operators using this Schrödinger evolution. Okay. So this is the first feature. So this is not that bad. What the only thing we say is that instead of Newton's second law, we're going to use this Schrödinger equation to write the dynamics of the system. If it was only that, it wasn't that bad. It's not so complex. It's a different equation, maybe. But the second feature is when we want to make quantum systems interact with each other. Then things become much more complicated, because then, for example, if you have n quantum systems, S1, S2 until Sn, and we want to make them interact with each other, then the state of this total system is going to be living in a Hilbert space, which is given by the tensor product of the Hilbert spaces associated to each of these systems, instead of a Cartesian product of these Hilbert spaces, as in the classical case. So if it was in a classical case, the dimension of the new state would be the sum of these dimensions, whereas in the quantum case, no, we have the product of these dimensions. And this is basically the whole, and of course this also leads to the fact that in quantum systems we can deal with entanglement. We have to deal with entanglement. We have states which cannot be written as separate state of each system, as a separable state of each, in each Hilbert space. So, okay, this is the main, I would say, richness and make complexity of a quantum system. The fact that if we wanted really to simulate classically such a quantum system, then in principle we would need a huge dimensional Hilbert space, and using a classical system to do this, it's hard. So that's basically the main source of trouble for classical simulations of a quantum system. And at the same time, this is also main resource for quantum computation. That's why quantum computation could be exponentially faster or more powerful than a classical computer. Okay, the fact that this making quantum systems interact with each other can let us explore a huge dimensional Hilbert space. And then there is the third feature, which deals with the measurement. So in quantum mechanics, measurement of any physical observable, any physical quantity, is necessarily a random and irreversible feature, as a random and irreversible feature. What does it mean? Basically, it means that to any physical quantity, basically we associate another Hermitian operator, so an observable O, which lives also on this Hilbert space. So as its Hermitian is diagonalizable, so we can write it as the sum of its eigenprojectors. So lambda mu's are eigenvalues, the p mu's are projection over the eigenstates associated to lambda mu. So whenever you measure this physical observable O, you necessarily obtain one of these eigenvalues as a result. So this is the random character. And you can achieve each of those with a probability given by this thing here. So you project the state of the system along the associated eigenprojector, p mu, and then you take the overlap with the psi itself. So that's the probability of obtaining the result lambda mu. And you see very well that if you sum over all mu's, you obtain 1 because the sum over eigenprojectors is identity. So because the eigenstates of a Hermitian observable expand the whole Hilbert space. Okay? So this is, the measurement outcomes are going to be random and given by this random probability distribution. And once you have measured the eigenvalue lambda mu, then the state in a irreversible manner is projected along the direction associated to that eigenvalue. So if psi was a state before the measurement, after you have done the measurement, the new state is given by p mu psi divided by its norm. So you project the state over this direction. So this is the random, this is the irreversible character of a quantum measurement. Okay, so basically, and so this is, of course, a little bit puzzling for measurement, and for example, for the concept of feedback control, if you're familiar with control in classical dynamics. Whenever you want to measure your system, you're changing the state of your system because of this projection. So, of course, this we have to know how. So basically, it means that when you want to, for example, stabilize your system, do something with your system, you should be careful about what you're measuring. You shouldn't measure anything. You should measure something which is compatible with what you want to stabilize. Otherwise, you're going to yourself basically bother that stabilization or make that because of this measurement, make it impossible to stabilize that state. And at the same time, so this is the puzzling part, and at the same time, this is also the main resource for quantum communication and cryptography. Okay, this fact that by measuring you perturb the state of the system, this is also the part which is used, the feature which is used in quantum communication and cryptography. Okay, so these are the three features. I think if you basically, with these three features, you can model any quantum system. Basically, by combining these three features, Schrödinger equation, entanglement due to tensor product, nature of interaction of quantum systems, and this randomness and irreversibility of induced by measurements are the three features you need to know if you want to write the equations for the dynamics of a general quantum system that is being measured, controlled, and manipulated. And so in particular, a quantum computer, which is a many-body quantum system, many bits interacting with each other. Okay, so very maybe fast introduction to quantum mechanics, let's say. And now let me go to quantum computation, but before going to quantum computing, I would need to explain what is classical computing. Maybe, and I'm talking about the hardware, so what is a classical bit? You use it, you have in your computer, on your cell phones, you have classical bits, but what is in practice a physical system associated to classical bit? A classical bit is nothing else than a strongly dissipative bistable system. You can think of a particle in a double potential well, satisfying these dynamics, m double dot x plus eta x dot plus, and this is the friction, plus some potential, derivative of some potential equals to 0. So this is what a classical bit is. It can establish, because of this friction, basically whatever you start, you're going to get into one of these two positions, which we call 0 or 1 of your classical bit. Okay, this is a mechanical analog of a classical bit. An electrical version, the one we actually have in your computers, for example, this is a static RAM cell, is such a system which is built out of 6 transistors here. So the 2 transistors here are only used to access this static RAM, to read and write on this static RAM. But these basically 4 other transistors coupled to each other actually implement such a bistable system where basically current going through this or there would, or this, or being means you have basically the state, the bit in the state 1 or 0. Okay. So what are the requirements for having such a classical bit? We need to have such a strong dissipation, eta, large eta, to make this system stable enough, go fast towards one of these two states. And then we need also this potential barrier, delta U, to be large enough, such that because of the thermal fluctuations, thermal noise that might be there, you don't have the probability of jumps from 0 to 1 or 1 to 0 becomes exponentially small. Okay. So this is this also comes at the cost of the fact that when you want to do operations, when you want to change 0 to 1 yourself, then you have to spend more energy. So a classical bit, you can make it more reliable, but at the expense of making it more, requiring more energy to do an operation on this bit. Okay. What is a quantum bit? So as I said, well, the first thing is that now instead of these Newton's laws, we need to use a Schrödinger equation. So basically, we're going to use a Schrödinger operator. So for example, a particle having a kinetic energy and a potential energy. So it's basically we have this operator minus h bar over to the power 2 over divided by 2m, m being the mass of the particle, Laplacian plus u of x. You try to discretize or find the eigenstates of this Schrödinger operator. And so, in principle, you have many, an infinite number. So, for example, you can imagine the case of a hydrogen molecule, the intranuclear distance between the two hydrogen atoms. This potential is going to be the one you see over here. And then when you try to find the eigenstates, you're going to see that, well, you have the ground state, first excited state, and then any state that you can imagine. And then, in principle, a quantum bit is going to be 2 out of these many states of this energy landscape, basically. You basically discretize or diagonalize this Schrödinger operator, and you take 2 of the eigenstates, and you call them your 0 and 1 of your quantum bit. So these are 2 wave functions now, psi 0 of x, psi 1 of x. Living in the Hilbert space, here is L2 of r, with values in C. And now any state that is in a superposition of this 0 and 1, C0 0 plus C1 1, where C0 and C1 are complex numbers whose sum of squares of the modulus square is equal to 1, is going to be a possible state of your qubit. Okay? Okay, of course, the hydrogen molecule is not a good qubit because of many reasons. It's not a very stable qubit. It's not something we would want to use. So people are working on various platforms to implement such quantum bits. So here I'm going to start by one platform which is particularly well, so one type of it is particularly old, but the other type of it is particularly new, and it's attracting a lot of interest these days. So basically, in the very early days of quantum computation, people started thinking as ions or charged atoms as a good way to have well-defined qubits. Why? Because as these particles are charged, we can trap them through some dynamic electric field and an electrical trap, and then address the state of these atoms, the electronic state of these atoms, by applying lasers, focused lasers on laser beams, for example, on these atoms. So this is basically one of the earliest platforms to make a quantum computer, trapped ions, and basically later on, basically through the past 10 years. Also, a new platform actually showed up, which is basically quite similar. It's just that the atoms are not anymore charged; they are neutral atoms. But they are now the whole thing developed because there was no new ways of trapping neutral atoms using optical tweezers. And here we had the possibility to do some further stuff. For example, shuttling the atoms around, or moving the atoms seems to be easier somehow. And some other properties, we can excite them to some energy levels, which makes interactions of these atoms quite easy, much easier than in the trapped ion case. And so this is now actually very one of the most promising platforms for quantum computing. So these neutral atoms in optical tweezers. In France, there is the company Pascal, who is working on this kind of technology, even though they don't have all the capabilities that state-of-art capabilities to do quantum computation yet, but that's one of the most promising ones. I'm not going to talk about this. This is not my domain of expertise. I'm going to mainly talk about the second platform, which is the platform of superconducting qubits. So here, basically, it's much closer to what actually a classical computer looks like. So we're gonna be working with electrical circuits. The only difference is that instead of semiconductors, we're gonna use superconductors. And we're gonna use actually the superconducting circuits in the frequency ranges. So basically we're gonna make superconducting resonators, LC resonators if you want, with frequencies within the same range as, not far from the frequencies that are of your cell phones. For example, it's in microwave frequencies, so 8 to 10 gigahertz. And we're going to use these devices to make a quantum computer. So here you see a particular case of such a superconducting circuit from Andreas Wallraff's group in ETH Zurich, which implements actually a surface code that I'm going to talk about later on. So which is actually maybe a first instance of a quantum error correcting code for, so basically each of these yellow dots that you see here is a qubit, and all the rest are basically are the devices that are there to read out, to measure these qubits, to control these qubits, and so here basically I think we should have 17 of these qubits. If we count, my count is good, then count them actually. Yeah. Okay. So what is a superconducting circuit, and how can we look at it as a quantum system? So let me look at this LC resonator. So you have an inductor in parallel to a capacitance. Okay. So you can look at it as a crystal of positive ions of nucleus of superconducting material, surrounded by an electronic condensate. Okay, so it's this cloud of electrons that are somehow oscillating around in this crystalline structure, if you want. And what is the quantum degree of freedom? What we want to look as a quantum degree of freedom is some kind of center of mass of this electronic condensate. So you have an Avogadro number of these electrons, if you want, the macroscopic number of these electrons. But their center of mass somehow, which is oscillating around this positive ions, can be still treated in some cases, under some particular situation, can be treated quantum mechanically. So and you see the size is here 1 millimeter. So actually it's a device you see by your eye. We are not microscopic level. We have a device which is quite big. We have a large number of electrons, and yet it can be modeled. It still needs to be modeled quantum mechanically. And when does it? The thing is that when we do go into a quantum regime, it's a matter of temperature, basically. So if you have, if such an LC circuit has a frequency of oscillation of about 5 to 10 gigahertz, then when you go to a very low temperature of around 20 millikelvin, you still need the quantum mechanics to model the dynamics of this oscillator. Okay? When you are using a less massive object, like a hydrogen atom, a single electron of a hydrogen atom around the nucleus, the frequency of oscillation being much, much higher, you can tolerate a much, much larger temperature and be still in a quantum world. Okay, so the fact that by going from a hydrogen atom to the LC resonator, we are still in a quantum world is just by reducing the temperature somehow. Okay? I hope. And so now I'm saying that we need quantum mechanics, but what does it mean? So we know that if we want to look at the position of this electron of the hydrogen atom with respect to nucleus, we need to use quantum mechanics. What does it mean? We have two conjugate variables, position and momentum of this electron. And then we write the Schrödinger equation for this position and momentum as conjugate variables. In the case of this LC resonator, the two conjugate variables are the magnetic field, magnetic flux through the inductance, or somehow the integral of the current through the inductance, and the charge across the capacitance, which is the integral of voltage across the capacitance. So when you have an LC resonator, you have an oscillation between the voltage and current. So if you consider the integral of current and the integral of voltage, they can replace the position and momentum of this electron of hydrogen atom. And then basically when you go to the quantum world, you satisfy this commutation relation between these two conjugate variables, phi and q, which means that basically you can look at q as somehow the derivative with respect to phi. So basically when we will want to write the Schrödinger equation associated to the dynamics of current and voltage in this system, we come up with this Hamiltonian, which is minus 1 over 2 times capacitance, second derivative with respect to phi, being this magnetic flux, plus phi squared divided by 2L. Okay? So it's a Schrödinger equation associated to a quantum harmonic oscillator. Okay? So this is if you wanted to look at it as a classical system, it was a classical harmonic oscillator. In the quantum world, it becomes a quantum harmonic oscillator. And this potential is Hamiltonian is given by what you see over here. And when you try to diagonalize this operator, you find these energy levels. As it's harmonic, you're going to see equidistant energy levels. So basically each eigenvalue, the separation of each eigenvalue from the next one is given by the same value omega r, h bar omega r, where omega r is the frequency of oscillation, 1 over square root of L times C. Okay? So basically this is how we make a quantum harmonic oscillator in electric volt with this superconducting circuit. As it's superconducting, we don't have any resistance. We don't have any, so we don't have any friction in principle. And so it's really just a non-damped harmonic oscillator, basically the harmonic oscillator, which is conservative harmonic oscillator in principle. But the LC oscillator, which is as being harmonic, is not a good qubit. Why is not a good qubit? Because, well, there is no way to address two energy levels. You have an infinite number of energy levels here, and once you try to shine some light on this, some microwave light, well, if you want to act on it, you have to make this field at resonance with this frequency, omega r. But when you try to shine this, to basically apply this electromagnetic drive to your LC oscillator, you're going to basically populate all the energy levels here, and not only two of them. So you cannot separate two energy levels from the rest of this. So you need to do something for that. And that thing is that you can make this inductor nonlinear. So basically by using a linear inductance and a linear capacitance, you have a linear harmonic oscillator, or basically a harmonic oscillator. And in order to make an unharmonic oscillator, something which has energy levels which are not separated by the same amount, you need to give some nonlinearity to your system, and that can be done through some nonlinear inductance. And the some nice feature of superconducting circuits is that they have a device. We have a device in superconducting world which is called the Josephson junction, which is actually a lossless nonlinear inductor. So because if you look at a diode, for example, it's a nonlinear element, but it's lossy. This diode lets the field go in one direction, the current go in one direction, but not go back in the other direction. But in the other direction, it's basically absorbing the energy. So it's a lossy element. Here we have a Josephson junction is some kind of inductor which has some nonlinearity without having any loss in principle. And what's that? What is in practice this Josephson junction? It's basically two superconducting electrodes which are separated by a thin barrier of insulator. For example, these two superconducting electrodes are aluminum electrodes which are separated by a very thin barrier of aluminum oxide. And this device itself, at low temperature, acts like a nonlinear inductor. What does it mean? It means that the current voltage relation is not anymore linear with this, for this inductor. You have some potential which looks actually like a cosine instead of a x squared. So you had, in the case of a, oops, what's going on? Somebody wrote in the slide. Thank you. So here you had, for an actually linear inductor, you have a potential which looks as phi squared. And here, this phi squared becomes a cosine of phi because of this Josephson junction. So you have minus Laplacian plus cosine of phi, which is like actually a pendulum. If you look at the potential of a pendulum, your pendulum actually has a nonlinear. So basically, a Josephson junction is the electrical version of a pendulum. And because it's not anymore a quadratic potential, it's an anharmonic potential. Now the energy levels are not separated equivalently. And now basically by applying a light at this particular frequency, you can just excite from this ground state to this excited state and not the other energy levels. And so this is going to be our quantum bit in a superconducting quantum computer. Okay? So this is how we would, so this is basically the conventional way of making a quantum bit in superconducting, like superconducting quantum bit. That's the way, for example, teams like Google, IBM, they're making their quantum bits. Like basically they are really using this kind of circuit, particular circuit, a capacitance in parallel to a Josephson junction that makes these two energy levels separate from the rest, and then by applying some microwave field at that frequency, which is in the order of 5 to 10 gigahertz, they basically excite, they do an operation between, they make the system excite from 0 to 1 or a superposition of 0 and 1, if you want. And this is how it looks like. This is some pictures from our lab. So we have, so our group is half experimental, half theory. And so we do basically experiments also on superconducting circuits. And so basically this is a picture of such a chip. So you see here you have maybe a few qubits. You could have a few qubits. You could have many more in the same size. And so the cables are connecting through these connections here. And you put this whole device on the bottom of this big device here, which is called the cryostat, or a fridge, if you want. So in these cans are shielding this device from the radiation coming from outside. And basically the hope is that the only connection to this device is through these connectors, through these cables which come out and this, from this fridge, and basically through to which we get access through some microwave generators or some amplifiers to read them out, and etc. Okay. So this device allows us at the bottom of this fridge to reach this temperature of around 20 millikelvin, which makes this device act quantum mechanically. Okay. So, okay. This is how we would like things to work, but the bad news is that, well, this quantum hardware is still too noisy, even though we have improved it by a lot through the past 20, 30 years. It's still very noisy. And where do we stand? If you take basically a classical RAM of your computer, basically it's quite a reliable object. It's now the probability of making an error when you do an operation is somewhere around 10 to the power minus 25 errors per gate per bit. So per operation per bit. So if you want to make a real error, you need to do many, many operations to 10 to the power 25 errors, operations before you see an error, a bug, in principle. In the quantum processor, the best ones today, this is somewhere around 10 to the power minus 3 to the 10 minus 4. So basically you can do about 1,000 or 10,000 operations before basically you make an error. You cannot go far with that. And basically for some at least for the algorithms for which we know there is some acceleration with respect to a classical computer. For example, for a Shor algorithm, we need somewhere around 10 to the power of minus 15. And for some easier algorithms than Shor, we might need 10 to the power minus 10. But we don't know, at least as my knowledge, we don't know any algorithm with a probable acceleration which could require less than this probability of error. Okay, maybe there are, but we don't know them. But so you see, there are about at least 6-7 orders of magnitude to gain between these errors and between these error rates, so that we can have a really reliable quantum computer in which we can run some algorithms with a probable advantage with respect to a classical computer. And this might appear hopeless because you should see that, well, we have basically gained about 2 orders of magnitude through the past 10 to 15 years, so 1 to 2, depending on the platforms. And so how can we hope to go how can we go that far? And the good news is that we don't necessarily require to improve each of these bits to get to that level. We can do something more with something else, which is called quantum error correction. Basically, the idea is that as soon as you get to these levels, you are good to start to do something else to make all of a sudden basically overcome this gap. And that's why people are excited these days about, basically they think that they are already there. They have some basic elements are there so that they can make now a computer which is that good. But that's, so I think the holy grail of hardware these days is really to make this error correction work, trying to make a fault-tolerant quantum computer. So you're going to have a course on quantum error correction by Gilles, I think. I don't know whether he's here. But so, Gilles Demar, so I think, not yet. But so I'm going to very rapidly give you some basics of quantum error correction. And so I think you're going to have a big course on that later on. So, well, the idea starts from classical error correction already. So even in classical devices, especially on classical communication, we already did, even in your cell phones, you use classical error correction. And what is the idea is that if you have a communication channel, you want to send some bit of information, classical bit of information, which is 0 or 1, well, this channel might be noisy. And this 0 and 1 might actually get flipped in this channel to 1 or 0 by some probability p, which might be small. And so how to correct this for these errors? The idea is that, the simple idea is that you can use redundancy. So instead of encoding 1 0 in 1 0, you encode 1 0 in 3 zeros and 1 in 3 ones. So you send 3 bits of information to send a single logical bit if you want. 3 physical bits encode a single logical bit. And what's happening now is that if you wait through the same channel this 3 bits of information, and each of them has a probability p to be flipped, of course, at the end you can do majority vote. Say, I look if a majority of my bits are in 0 or if a majority of them are in 1. And then the probability of making an error is that the probability of having at least 2 or 3 errors in these 3 bits. And this probability is going to be given by this value, which is of order of p squared. If p is small, it's of order of p squared. So basically, you have gone from p to p squared. So we have reduced the probability of error by repeating the information. And actually, as soon as p is smaller than 1/2, this logical probability of failure is smaller than the initial probability. Okay, you make less errors. And if p is more than 1/2, then you are really bad because it means that you could have just changed the definition of your 0 and 1. Yes?
Is the error correction computationally expensive?
Oh, sorry?
Is it computationally expensive?
Is it computationally expensive to do?
Error correction.
It's not, well, it's just, it takes, no, so it's basically your, the idea is that by increasing polynomially the size of your memory somehow, you're decreasing exponentially the probability of errors. So no, it's efficient in principle. So basically, you see, Is it clear? So basically here, by going from 1 to 3, basically we have gone from p to the power 2. So if you go to 5, you go to the p to the power 3, because you need at least three qubits to flip. So you, for example, here if you increase linearly the number of bits, you decrease exponentially the probability of error. Okay? So that's the principle. Of course, this is what's called the repetition code. In classical error correction, there are much better codes than repeating only the bit, because basically you could use many bits, many physical bits to encode many logical bits in a redundant manner somehow, and you can have better ways of encoding, but at least this is one way to do it. Okay, so this is the general idea of error correction. In the quantum world, though, things become more complicated because of the features I explained at the very beginning of the course. And what are those? Well, the question is how to detect errors without destroying quantum information. Okay, so basically, if you're in the quantum world, you are working with this superposition of these states, 0 and 1. And if you come and ask your bit of information, if you're in 0 or 1, for example, if you want to do some majority vote, then you are projecting it on 0 or 1. You're going to read basically this precious quantum information, which was this superposition, you're going to basically erase it by measuring this bit. So you shouldn't measure the bit. You should measure something else, maybe. You're going to see that. The second problem is that the errors are continuous now. The errors are not 0 becoming 1 or 1 becoming 0. You could have, for example, so this is what we call a Pauli operator sigma x. So sigma x is basically the matrix 0, 1. So maybe I could use, so the operator sigma x, is it good here? Can I write here or? Yeah. Is the matrix 0, 1, 1, 0. So, which basically inverts the two states 0 and 1. Okay, so here psi lives in the case of a qubit, psi lives in C2, so it's a vector of dimension 2, and sigma x is what changes the two states 0 and 1. So basically, classical error would be just psi going sigma x psi. But in quantum, you could have actually any rotation around the sigma x axis of your qubit. So you could have any continuous rotation around sigma x axis. So it's not only sigma x, but any exponential I theta sigma x, where theta is an angle from 0 to 2 pi. So any unitary operator of this form can be an error on your system. So you have a continuum of errors to correct. And the last problem is that the errors are not only bit flips. They're not only sigma x. They could have could be other type of errors. For example, the phase between 0 and 1 could change as well. For example, you could go from C00 plus C11 to C00 minus C11. So it's a different type of error. So it's a rotation around z axis, for example. Okay. Of your qubit. So, okay, how to deal with all this? Okay, so the first question is that how to detect errors. So let's assume that for now, errors are only bit flips, like classical bit flips. But how can we do something like a repetition code, but not have this problem of detection, which makes this superposition collapse to either 0 or 1. So the idea is that instead of so we can still get inspired by classical error correction and now encode 0 by 3 zeros. So 0 tensor 0 tensor 0. So when I write 0 0 0, it means plus C1 1 tensor 1 tensor 1. So basically it's an entangled state of 3 qubits now, which is encoding a single. There is an error. There is a question, I think. I don't know. Should I?
Just a comment.
I guess I come. Okay. We do repetition by entanglement. So basically, instead of encoding information in the form of C00 plus C11, I use C0000 plus C1111. And now, so okay, the information is still there. The question is that what do we need to measure? So now let's assume we have waited some time, and this C0 0, 0 plus C1, 1, 1, 1 has now maybe jumped to the state C0, 1, 0, 0 plus C1, 0, 1, 1. So one of the bits has flipped. How can we see it? Of course, we shouldn't come and do majority vote. We should not measure all the qubits and say, is this majority 1 or majority 0, because then we're going to erase the information on the superposition. What we need to do is to measure something more clever, and that's these parity observables. So basically, sigma z tensor identity. So what does it mean? Sigma z tensor identity asks whether the first qubit and the second qubit have the same state, are in the same state or not. So if sigma z tensor identity is 1, it means that the first and second qubit are in the same state. If it's in -1, if it takes value -1, it means that they are in opposite states. And the same thing for identity sigma z. So basically, we measure the parity of the adjacent qubits. And so we have 2 bits of information. This takes us +1, -1. This gives us +1, -1. You have 4 possibilities, either both +1, which means that there has been no error. The first one -1, the second one +1, which means that the first qubit has flipped. The first one -1, the second one, the first one +1, and the second one -1 means that the third qubit has flipped. And if both are -1, it means that the middle qubit has flipped. And so you're going to correct for that. So you need to measure this parity to be able to correct for this bit flip error that you have there. Okay, so this is something you can do. But the important thing is that physically you need to be sure that you're measuring this observable and nothing else. Otherwise, you might be actually collapsing this superposition. And so you have to be careful to what to measure, really basically find a way to measure really this parity and nothing else. Yes?
We have only 2 qubits?
Here we have 3 qubits, and we measure these 2 parity checks. And so this is the first issue. Now the second issue, as I was mentioning, was that you have this yes. So this is the fact that the 2 other issues, that the fact that the errors are continuous and they are not only bit flips. And how are we going to handle them? And for this, I need first maybe to go very rapidly explaining what is an error in general, how to model errors in quantum mechanics. And for this, I need to go a little bit further than the language of wave functions. Okay, I need to use a different notation for the state of a quantum system. That's the notation of density operators or density matrices. Okay, so when we deal with a quantum system which is interacting with this environment, which is not in a closed world, which is not alone and isolated, then we cannot model it anymore by a wave function in a Hilbert space. We need to model it by something more elaborate, which we call a density operator, and which is shown here as this row. So it's an operator, it's a Hermitian operator in this Hilbert space, which lives actually in the space of what we call trace class operators. So operators which are L1 somehow. So if you, as it's Hermitian, you can diagonalize it. And you look at the sum of the absolute values of the eigenvalues, and it should be convergent, this sum. So this is basically these trace class operators. So the trace is well defined for this operator. So it has to be an operator which is Hermitian, trace class, semi-definite positive. Yes?
Just to clarify, inside the accolade, you should only use psi and not rho.
Yeah, sure. I'm sorry. Psi dag equals psi. Yes, I'm sorry. Psi, yes, this is psi is in B1 of H, such that psi dag equals to psi, semi-definite positive, and trace of psi equals to 1. Okay, so instead of using wave functions, which was basically elements of Hilbert space of norm 1, here we are going to be working with operators, trace class operators, which are Hermitian and semi-definite positive and of trace 1. So the case of a wave function is a particular case where this row is actually can be replaced by a projector over this wave function. So it's a rank 1 operator. Okay? So if you have a rank 1 operator, then you can use the wave function language because you can go to the eigenstate associated to that rank 1 eigenstate. And that's going to be your wave function. So this is the case of a closed quantum system. The pure quantum system is pure quantum state is a state associated to a density operator of rank 1, a single projector over this state psi. But in general, when the system interacts, the rank is not going to remain 1, and the rank is going to increase. And so we cannot anymore use a single wave function to model the state of our system. Okay? We have to go beyond basically rank 1 operators. And now how to model errors. So we have a system and its environment. Error is interaction with the environment somehow. Okay, so some environment induces some noise on your system and makes an error on your system. And how do we model this? We have a system and then its environment. They live each of them in their Hilbert space. So you have the Hilbert space of your system and Hilbert space of environment. And so what error means, it means that basically you have your system. Maybe initially your system in some state rho s, the environment is some state rho environment. They interact with each other through a unitary evolution, a Schrödinger equation, so which generates a unitary evolution, the u of t, that might make them entangled to each other, because the unitary evolution which makes them interact with each other might make them entangled. And then you're interested in only the state of your system because you don't have access to the state of environment. So you want to take the partial trace. You want to remove the environment from this. You take a partial, what we call a partial trace with respect to environment to go back to the Hilbert space of your system. And this, you can write it, you can show that this is necessarily, is going to be of the form sum of k, some operator, error operator ek rho s ek dagger, where the sum of ek dagger ek's is equal to identity. So these ek's are bounded operators on your Hilbert space of your system, such that the sum of ek dagger ek equals to identity. Why do you have this property? This is because u of t is a unitary operator. U of t being unitary means it preserves the basically the length of vectors. And this, when you do the math, you can show that this boils down to having the sum of ek dagger ek's equal to identity. And these are what we call the cross operators. Okay. So this is how we model an error in general in a quantum system. So we have an error process is given by a set of these operators ek, the cross operators, and a rho s, initial state rho s. After this error process goes to sum of ek rho s ek daggers. Okay.
Just a naive question.
Yes.
Ek is a row vector.
No, ek is an operator on the Hilbert space. It's a bounded operator on the Hilbert space.
Operator, and then the round e, is it a scalar kind of quantity, or is it?
Epsilon is a super operator. So this e is a super operator. So when I use this calligraphy, it's a super operator. It's something which sends a density operator to another density operator. And these capital EKs are operators. So these are B of H. And this is a super operator, something which goes from B1 of H, B1, to B1 of H.
HS or H?
HS. Yes, sorry.
Okay, thank you very much. Sorry.
Yes. Yes, thank you. Okay, so, and what is quantum error correction in a nutshell? It's some inversion operator. Somehow we define a subspace of this Hilbert space, HC. So for example, two-dimensional subspace of this bigger Hilbert space H system. And we call it a code space, HC. So it's a subspace of this large Hilbert space. And we try to find a recovery operation, some R of rho, which is itself something like a noise. So it's also sum of rho k, RK daggers, such that if you start from a rho in this subset, and you apply first the error and then the recovery, then you go back again to the rho C. So it's basically so you use you have some error which acts on your Hilbert space of your system, but it is basically recoverable or is correctable on a subset of the subspace of your system, of your Hilbert space, through some operation that you know, some action of the same form. So you can apply, this is something you apply, and this is something the environment applies to your system. But after each time the environment acts on your system, you apply this, and you go back to your initial state. So this is the quantum error correction in the nutshell. Now how it works, this is very theoretical. So basically, first, how does it work? Before, why does it work somehow? In some sense, so this was basically some observation by Peter Shor, which basically somehow started the whole field of quantum error correction. The fact that if you have a recovery operation that corrects an error channel epsilon, so you have an R which corrects for epsilon, so which means that for any rho C, R of which is in this subspace, R applied to epsilon of rho C gives you rho C. Then the same recovery operation corrects any other error channel F, such that its elements Fk are linear combinations of Ek. So you see, if you go back to the previous slide, I said for this epsilon, I have these elements Ek, which model how the error acts. Now if I replace this E epsilon by another F error, such that it is given by Fk's, but Fk's are linear combination of these Ek's, and if you have a recovery that corrects E, then it corrects also F. So this is just some very simple linear algebra that you can do, and this is because of linearity of all this. It works very well. And this simple fact makes error correction work. Why? Basically what it says is that when you deal with qubits, you can generate any 2 by 2 matrix, if you want, by these 4 matrices, the Pauli operators, identity sigma x, sigma y, and sigma z. So you need only to find a recovery operation which corrects only for these discrete errors, identity sigma x, sigma y, and sigma z. You don't need to correct for continuum of errors. You just need to correct for these 4 errors. You have a recovery operation. This corrects for these 4 operations, and this corrects anything.
When you say it corrects the error, you mean the probability of having error would be 0?
So yes, it would be 0 if your, yes.
Can you repeat the question?
Yeah, so the question was that when you mean it corrects the error, does it mean that the probability of error is 0? So the answer is yes, as far as your error is really only epsilon that I have said here. But the problem is that this is only an approximation in practice. So basically here, for example, this epsilon, one case is, for example, you have a 3-qubit code. It's only one error. So epsilon is possibility of having 1 error on this 3-qubit code. If your possibility was only having 1 error during this time, then you will correct it with probability 1. But the problem is that this is an approximation of reality. If you wait for some time, you always have also possibility of having 2 errors or 3 errors, so which is the probability of those that are not 0. So if your error channel is really something you know, you can always find a code for that, and basically then you correct for any superposition of any combination of those errors as well. So okay, so this is the good news that Shor found for us in 1995, basically, and which launched the whole idea of error correction, quantum error correction. So you only need to correct for these discrete errors, identity sigma x, sigma y, and sigma z, to be able to correct for anything. And so from there has been a bunch of codes that have been proposed. I'm not going to go through the history of codes. So there are a lot of them. Maybe Gilles is going to talk about that. But I'm going to tell you about the surface code, which is somehow the most conventional one these days. So a lot of people are going to trying to implement them. The Google team, IBM team, IBM has not switched to another code, but Google is now still working on the surface code. And the idea is somehow is generalization of the repetition code. So in the repetition code is a code which was there to correct for sigma x errors. And here basically we want to correct for sigma x errors, sigma y errors, and sigma z errors. But look, sigma y, sigma y is nothing else than sigma x times sigma z. So if you have a way to correct sigma x errors and sigma z errors, you have also a way to correct sigma y errors together, because if you remove them separately, basically you have also removing sigma y errors. So basically the idea is that instead of using a line of code, a repetition code in one dimension, you use a repetition code in 2 dimensions. One for correcting sigma x errors and the other dimension for correcting sigma z errors. And this is going to correct for any error, basically. And so this is how it's represented here. So you have a bunch of qubits. So each white circle that you see here is a data qubit, what we call a data qubit. So this whole patch of qubits, which should be about, if I'm not mistaken, it should be about 50 qubits, maybe more, I don't remember, is encoding a single logical qubit. Okay, so you're using many physical qubits to encode a single logical qubit, which is error corrected. Okay, so we are living in a Hilbert space of dimension huge, 2 to the power 50. This is HS, thank you. Thank you. So if I go back to my notations before, see the HS has a dimension 2 to the power 50 here. But my HC, the code space, is dimension 2. So it's a 2-dimensional subspace of a huge dimension to the power 50 Hilbert space, which is error corrected. See. Up. So what's the idea? You have these the white circles are each of them a single physical qubit. And what we would like to do, so if you remember before, in the case of a repetition code, we were measuring sigma z parities between each adjacent qubit. Okay, here we're going to use sigma four-way parity checks of sigma z's between, you see, between this one, and this one, for example. We measure the sigma z, tensor sigma z, tensor sigma z, tensor sigma z of these 4 qubits. The same thing for every green cross. And the same thing for the sigma x parities of the yellow crosses. And it turns out that we can measure all these observables together because they all commute to each other, with each other, these observables that you see here. Okay, even though sigma x and sigma z do not commute with each other, when you look at these operators, for example, this one and this one, they have 2x and z's, so they commute with each other because x and z anti-commute. When you have 2 of them, they commute. So basically, you can measure all these observables at once. And if you do the math, you see that you have basically this number of data qubits and this number of independent constraints because of these measurement results. So we have basically 2 times d minus 1 plus 1 qubits and 2 times d minus 1 independent measurement results. There remains only 1 degree of freedom, and that's the qubit that you have encoded. So you will start with a dimension huge space, but because of all these measurements, you project it on a 2-dimensional Hilbert space. That is your logical qubit. And basically the idea is that now by measuring these continuously or stroboscopically these observables, x and z observables, you can know where the errors have happened and correct for them. Basically, the only error that you're not correcting is that during one round of measurements, you have errors going from one edge to another. So for example, if you have sigma z error on all these qubits, then you're not going to see it. This is going to be actually a logical sigma z operation, basically something which sends your logical 0 to the logical 1. That's something you cannot see. But the probability of that happening is very small. It's the p to the power 5, because you have, here we have a distance 5 code. So you have to have 5 of these qubits to go an error at the same time, so that you have a logical error. Okay? But that also tells you how to do operations on this logical bit. It means that if you want to invert the state of your logical bit, for example, you apply a sigma x logical, you need to apply a sigma x on all the bits of a line going from one side to another side. So it could be any of those. It could be this one, for example. If you want to do a sigma z operation, you do a sigma z operation on all of these bits. And that's going to do a sigma z operation. But these are only symbol operations. This means only sigma x or sigma z, but how we're going to do exponential I theta sigma x or exponential I theta sigma z, and that's the whole problem of fault tolerance. So I don't know how much time I have to go through that. I have 20 more minutes? Yeah. Okay, so I have... So this is what people try to do. So people trying to implement these codes, these many qubits, measure them continuously, based on this measurement results in real time, realize where there are errors and correct for these errors. So this is whole complexity of this thing. And this is just to make a single logical qubit. Okay. And how do we do this measurements? If you remember from the very beginning, I mentioned that you need to be sure that you're measuring really these parities, sigma z tensor sigma z's, or sigma x tensor sigma x, and nothing else. Otherwise, you're gonna erase the information. And so that's very important how to do this measurement. So for example, to perform this parity measurements, they add these black dots, which are another qubit, which we call measurement qubits or ancilla qubits. And basically, we prepare these measurement qubits in some state. We perform some logical operations, some CNOT operations between these data qubits and this logical operation, and then we measure this ancilla qubit. We never measure the data qubits themselves. We measure really these ancilla or measurement qubits that are interacting with our measurement qubits. And then we do that measurement. And as these measurement results, they are faulty usually, because this qubit itself can undergo an error during this process, or the measurement itself is not perfect. Then you have to repeat these measurements many, many times before you decide what is the result of the measurement as well. So there is a whole process of decoding based on the fact that the measurements has errors, the qubits have errors, and these gates have errors. And so how to deal with all of that. We have the whole decoding procedure based on that. And this is basically how it looks in practice, as I showed you in the various earlier slides. So this was one of the early experiments. So you see the earlier experiments in 2022. So this is quite new. So from ETH group of Andras Valraff. Well, they realized that distance 3 code, basically you have 9 data qubits and 8 measurement qubits, so 17 qubits, where I told you there are 17 of them. And basically it's not very readable here. What is important is this measurement error. So this is how it looks like, actually. So you need to do, so these are the data qubits, 9 data qubits, and these are the 8 measurement qubits around. And you need to do all these kind of gates to these measurements. And each cycle of error correction, each measurement cycle takes about 1 microsecond. And basically you need to do error correction then at this level. So basically you need to decode this information rapidly as well in the classical electronics and decide where to correct errors. Okay, so what is the promise of surface code? So promise of surface code is that, this is well explained in this figure here. So what you have in the x-axis is the per step error rate. So what it means per each step of error correction, what is the probability of error of each operation. So you have these CNOT operations, you have these measurements, you have this preparation of the ancilla, all these operations, each of them have some error probability. And even idle time, waiting for some time without doing anything on the qubit, have some error as well, because there is this qubit during this time, it could decohere, it could lose information. So this probability of error, we call it per step error rate. So this is the physical error rate. And on the y-axis is what we get by error correction as logical error rate. Okay? So, and what you see in different colors is the distance of the code, the size of the patch that encodes a single logical qubit. So the idea is that if you're below some threshold value, which is somewhere around 0.5% for physical errors, then by increasing the size of the code, You see, this is in logarithmic scale. By increasing the size of the code linearly, or quadratically, because this is the distance, but it's a square, then you decrease the error probability exponentially. So that's the promise of error correction with surface codes. So you're increasing quadratically the size of the code, and you decrease exponentially the logical error probability. So this is nice news, but you need first to reach for all operations a fidelity, an error rate below 0.5%. You need to be sure that all the operations that you want to do, you can do them at with better errors than 0.5%. And that's why I said 10 to the power minus 3 made people actually quite happy already. So it's basically when you have a probability of error of 10 to the minus 3, they say, well, if we can now put a lot of them together, we might be able to make this work. And that's why people are trying to make this work now. So basically, this is the formula. It says that logical error probability is going to be given by p is going to be proportional to p divided by p threshold to the power d plus 1 divided by 2, d being the size of this surface code. Okay? Okay, and so where is the state of progress? So the best the state of art is by Google team. So there is this paper that appeared this year in Nature, where they actually showed this error correction working, really. And basically, what do you see here? So this is actually the state of their experiment 2 years ago, and this is where they are today. So you see the improvement. So what do we see here? This is the error correction cycle. So time, basically, time evolving. So you have here, they have done 200 rounds of error correction, if you want, until here. Here is logical error probability. How much probability of errors? And what is the probability of errors after 200 rounds, if you want here. And these different colors are different distances of the code. So they have implemented a distance 3 code, I'm sorry, this is the red one, distance 5 code, and distance 7 code. And what you see is that the decoherence rate, the logical error probability decrease when you increase the size. So that means that error correction is working. But how much does it increase is traced here. So it says that they say that each time I increase the distance by 2, I decrease the error probability by a factor of 2. By a factor of 2. So basically it means that this p divided by p threshold is 1/2, basically. So they are a factor of 2 better than threshold in average for all the operations, because we have made a lot of operations. And in general, this whole thing works like a surface code where physical error probabilities are about a factor of 2 better than threshold values. And that's basically the state of art on this topic. And so this is, if you want, they have a plot where they explain for each of the operations they need for this error correction, where they lie in as an error probability. So you see 1-qubit operations are quite good. The 2-qubit operations are here, so it's about 0.5% actually. So they are you have a distribution because you have many qubits, and not every operation has the same fidelity. Some qubits are better than the others, so you have a distribution of error probabilities. And then you have measurement and idle. So these are operations that take much longer time, so they are more susceptible to error. But in practice, the average behavior of this operation together makes you a factor of 2 better than threshold. And that's why the error correction is working. And what you see is that in 2023, basically they had distance 3 and distance 5 code, and they didn't see any improvement. Basically, they had the same value because they were only at the level of threshold, basically, and they had improved things 2 years by a factor of 2, basically. And so they are now here. Okay, so if you go back to this plot, there we can then have a second plot which says how we can anticipate things. So I told you that if you want to start to do algorithms which are interesting, then you need to go to the level of 10 to the power minus 10 logical error probability. So what is this plot? It shows you where are you with respect to this threshold value for your physical error probabilities at the on the x-axis, and how many qubits, physical qubits, do you need per logical qubit to get to that 10 to the power minus 10 level. So today, Google is here. I mean, today or 6 months ago, they are here. So it means that if they wanted to get to the 10 to the minus 10 level, they need 10,000 qubits, physical qubits per logical qubit, to make this work, to get to the 10 to the power minus 10 level. So if you want to know how to run an algorithm over 1,000 physical logical qubits, then you need 1,000 times 10,000, so 10 million physical qubits that are all at this level of performance. Of course, we can hope that as they have improved things in a matter of 2 years, by a factor of 2, maybe they can get to this level of 10 minus 1 in the near future. It's plausible. But even there, you need something about 1,000 physical qubits per logical qubit, so a factor of 10 improvement, but still a lot. So that's why this is like sending human on the moon. I think it's a very hard task, so it's not a simple thing to do. And we need to expand this, make these huge systems, while keeping each of these systems controllable and with a very good coherence, with a very good error probability. And so this is not an easy task. Okay, so I have some slides on, so this is only how do we do a good qubit, but we didn't say how do we do operations on this qubit. And this is a whole concept of fault tolerance of gates. So I'm going to skip that because this is going to take me a while. So I think this is the concept of lattice surgery to do operations, and then magic states for doing various gates. So I'm going to skip this part, I guess. So how do we do gates on such a device? So I'm going to more switch to, so this seems very hard. So maybe people with an infinite amount of money, like Google, could do that. Could hope to do that in the near future, but there are people who have less money and who think about other ways to do this. And so I'm going to try to somehow explain what are some of approaches to reduce this hardware overhead to get this fault tolerance. So with this fault tolerance. So the first thing that you could do is try to design new qubits. For example, new superconducting qubits, which have some kind of intrinsic protection against errors, such that right away you are better than factor of 10 below threshold, maybe for this surface code, like factor 10, 20, 100, maybe better than threshold. So there are some ideas around that. So I'm not going to go very much into the details of this. So there are a lot of candidates for making such qubits, and people around the world are working on them. Fluxonium, COS2 5 qubits, 0 pi qubits. These are qubits that by some symmetries people try to make them robust with respect to dominant sources of noise, for example, charge noise, flux noise. They try to remove basically the effect of error directly at the hardware level on the system, on the qubit, before trying to scale with them. So Transmon, which is the one used by Google, is already quite a good one, but there are ways people have, at least theoretically, there are ways to make better qubits, and people are trying to make them. So that's one way, but which is maybe the most straightforward in some sense way. Better try to make better physical qubits so that quantum error correction needs to correct less errors somehow. The second way is to make better codes than surface code. And that's what I think Gilles is going to tell you about. So, because actually what people have shown is that surface code is actually not okay. No, yeah, people have not shown it's actually quite straightforward to see that surface code, when compared to the classical codes, is actually very bad code. Basically, as I was mentioning, it's coming from the fact that repetition code is a very bad code in a classical code. Because when you increase the number of physical qubits, the physical bits, for example, to encode a classical bit, you might be able to encode many logical bits in the same chain of physical bits using the same redundancy. You don't need to think always in the way I want to encode a single logical bit or qubit, and I'm going to use a bunch of atoms, a bunch of qubits. You could use a bunch of qubits to encode a bunch of logical qubits. You could use this idea. So basically, instead of using many patches of surface code to encode for each of them a logical qubit, we could try to have a single patch of surface code somehow encoding k logical qubits. So directly use the same surface code, the same amount of resource to encode many logical qubits. So somehow some of these physical qubits are going to be used in many logical qubits somehow. And so this is the idea of, the main idea around this is given by low density parity check codes, which are some codes where basically the parity checks that I was mentioning, this XXXX, remain of low density. So here it was weight 4, so we don't want to increase this weight much more than 4. The question is that how can we make better codes than surface code with that? And so actually we have this notation of NKD codes. N stands for the number of physical qubits, K stands for the number of logical qubits encoded, and D is this distance of the code, how good it corrects errors, how much errors does it correct somehow. So if you look at the surface code N is N, K is 1, and D is the square root of N. Okay? Basically, this is correct square root of N errors for a single logical qubit with N qubits. It appears that there is a recent theoretical development, so it's from 22, and in particular by Gilles and Antoine Leverrier, which shows that you can have LDPC codes where this K is of order of N and this D is also of order of N. So there is a huge room for improvement, you see, between surface code and that. So you can go from encoding only one logical qubit to encoding something of order of N qubits, logical qubits, with a distance of order N, square root of the square root of N. So it's, of course, much better than the surface code. The bad news is that it's not going to be easy because if there is some physical constraints. So in superconducting circuits, you have to put your qubits on a chip. And the chip is a two-dimensional object. And so you have two-dimensional connectivity constraints between these qubits. And then there are some limits. So for example, this theorem, there is a theorem by Bravi, Poulan, and Terral, which says that in this NKD notation, K times D squared needs to be in a 2D setup. It needs to be smaller than something of order of N. Which means that, well, actually the surface code is actually saturated in this bound. So in the 2D, we cannot do better than surface code somehow. That's why people like Google have decided to work with surface code. So we know that to have better codes than a surface code, then we need to go beyond 2D, or have some kind of long-range connectivities in the 2D. And that's what people in IBM are trying to do these days. Trying to do a surface code, but with some connectivity, making some cables across this chip, try to connect qubits which are far away. And then they can show that you can have a lot of improvement. So for example, this code, this is IBM cross code. This is a theoretical result published in 2024. They showed that with 144 qubits, so 12 by 12, they can, in principle, you have, if you were to use it as a surface code, you would have had a distance 12 code, which encoded a single logical qubit. But this one, with these new connectivities, so there are many of them everywhere, long-range connectivities, encodes 12 logical qubits with distance 12. So you have improved by a factor of 12 the number of encoded logical qubits, just adding these connectivities. But it means that you need to develop new hardware. You need to develop new long-range connections between these qubits, and that's what IBM team is working on. So maybe this is one way of, this is the second basically shortcut possible, and some people are working on this. And the third shortcut, that is the one we work on, I'm not going to have much time to talk about, is about using some kind of bottom level error correction. So instead of using qubits to encode information, we are going to use harmonic oscillators to encode quantum information. So if you remember from the very beginning, I told you that a harmonic oscillator is not a good qubit because you cannot address two states of this harmonic oscillator. But it actually turns out to be actually a very good system to encode information because it has an infinite number of energy levels, and you can use this infinite number of energy levels to give to have the redundancy you need to do error correction. If you do it in an intelligent manner. So I'm going to go very rapidly over this. So basically, the idea that we follow in our group, and some other teams in the world also use that now, is that we're going to encode information in what we call the coherent states of this harmonic oscillator. So, so these are what we call the cat qubits, basically, the Schrödinger cat state. So we don't anymore use energy levels of a harmonic oscillator, but we use the oscillation. So it's looking like you can think of a pendulum which is oscillating, and it's oscillating with two possible phases. So it's a phase of oscillation that is going to encode information. So basically, you could imagine your pendulum at time 0 is here or it's here on the opposite phase, and it's oscillating. And these are going to be the zeros and ones of our qubit. And why is it better? Because we have a way to actually stabilize this. So basically, I can show you the idea on this video. So you have a pendulum connected to a spring. The particular property is that this spring has a frequency which is twice the frequency of the pendulum. Okay, we have chosen this such a that this is happening. And then we apply a forcing on the. So I do it once again. So we derive the spring, and it starts driving the pendulum. And because of some friction that we add ourselves to this spring, we can actually have a steady state oscillation of this pendulum because of this friction. So the friction, we add ourselves some friction to make this stabilize around some particular amplitude of oscillation. Okay? The nice property is that as this frequency of oscillation is twice the frequency of the pendulum, this is actually going to be a bistable system. So if you start, so you see wherever I start, from whatever phase I start, I'm going to stabilize around two opposite phases because of the fact that this the frequency of the spring is twice the frequency of the pendulum. And these two phases are going to be the zeros and ones of our bit or our qubit later on. Okay? So that's the general idea that we follow. The nice property is that now if you look at these two opposite phases that are stabilized by this friction, if I come and basically don't show you what's happening down there, on the top you don't see any difference. So which means that the friction that is there does not get any information on whether your qubit is in the state 0 or 1. So it's a way to basically have stabilize a qubit along to the two states 0 and 1 without this stabilization or this friction getting any information on whether it's 0 or 1. And that's what you need to make this work, this classical system work in quantum work. Okay? So this is the thing that we actually engineer in our lab, and also, so basically there is this company in France which is called Alice and Bob, which is basically a spin-off of our team and the team at INS Lyon, which actually are now implementing these devices, these kind of qubits. So basically electrical version of this system that I showed you, and which turns out to be a bit, a quantum bit. So I'm going to go very fast on this. A quantum bit, which is actually a very good classical bit to start with somehow. So it doesn't have any bit flips. Because these, in fact, the thing is that if you look at the movie that I was showing to you, if I start and giving a kick, some error, on its phase being on the right, it's not. You have to give a very big kick such that it ends up on the left laterally. Basically, because of this friction, it's getting stabilized permanently somehow around this left or right state. So the possibility of making a bit flip is exponentially suppressed with the amplitude of oscillation. So basically you have a quantum bit which doesn't have bit flips, which only have phase flips. So you have only one type of error to correct instead of two types of errors in principle. So for now what we have shown in the experiments is that indeed this is the case. So by making the amplitude of oscillation larger and larger, the probability of bit flips gets exponentially better. So basically a state of art is that now the cat qubits that are made by Alice and Bob they have bit flip times of order of minutes to a few minutes. And the phase flip times are now of order of microseconds, and now you need to correct for phase flips. So for example, if you wanted to go back to the idea of surface code, now you need again just a repetition code maybe to correct for that. So you go from a d squared physical qubits to d. So you need you gain basically a square root factor. So if you needed 10,000, you need 100 now, maybe. So that's a hope, and so that's one. So of course there is much more to this, because then you need to do operations on this bit without introducing back this bit flip errors that you have suppressed. So and that's something we work on. So basically, theoretically we know how to do it, and experimentally they're trying to implement those. And so yeah, maybe that's basically where I can stop. Don't think I have a particular. Yeah, I have this slide, but so this is the approach that is also followed by Amazon as a company. So they are also working on cat qubits now, and they have this paper with a repetition code out of 5 cat qubits, but they represent basically similar results to Google team with this repetition code. So maybe I can stop here and answer some questions. Thank you.
Thank you very much. We can take some time for a quick question, and then we have the coffee pause. Question or comment or remark? Can we have your slide? Can you
Sure.
put your slides on the website?
Yes.
Yeah. Okay. Thank you, because it will be very helpful. Okay. So if there is no question, we have a. Okay.
Thank you. Hi. I think I understood how to measure that there was an error, but I didn't actually understand how to correct the error once we measured that there was an error.
That's so basically what happens is that when we measure this by measuring these observables, parity checks XXX and ZZZ parity checks that I was mentioning, then you project your errors to only sigma X or sigma Z type error. So basically, you know that now when you look, what you need to do to correct these errors is to apply a sigma Z X operation or sigma Z operation in some of your physical qubits. You just need to inverse the state of one of these qubits or the phase of this state of these qubits, and then that you can do it by single qubit operations. So that's what you need to do. But indeed, so the fact it's not, as I was mentioning, the errors are continuous at the beginning. But when you do these measurements, these parity checks, you project these continuous errors to actually discrete errors of the form sigma X or sigma Z. And then you need only to apply sigma X or sigma Z operation on some of these qubits.
Okay, so we go to the pause. Another one? Okay.
Thank you very much for this interesting talk. The final question about how do we compare the cost of adding these measured qubits or logic qubits with the gain that we can have in terms of error reduction? So
yeah, so that's basically the idea is that we want to make sure that to decrease errors, we have a polylogarithmic cost always for that, which means that basically by increasing the size of the code polynomially, you decrease the error probability exponentially. So that's the idea of error correction in general. The question is that now, what is the degree of that polynomial? What are the coefficients there? How we can improve that? That's a whole part that you try to optimize. But we know that it's so in principle, by increasing polynomially the size, you decrease exponentially. The question is, the details of that, and that's why surface code is a good code because it has a good threshold. It's possible in 2D connectivity and everything, but it's not a good code in the sense of how many logical qubits in code. And so, I think that's a question that needs to be, basically if you have better hardware, you can do better codes. That's usually what happens. So,
Okay.
Sorry, just last bit. Try to make it really short. Thank you. Just one question, question about difference on comparison between superconducting and silicon spin. Mm-hmm. I know your topic is not about the silicon spin, but probably you know much more than us. So if you can give us just an overview about
so
the two technologies.
Indeed, so one of I just mentioned these two platforms. atoms, basically, or either charged or neutral, or superconducting circuits. But indeed, there are many more platforms that people are considering to make a quantum computer. And one of those is semiconductors. The main reason for that is that you have this huge infrastructure of semiconductors that is already there, and how can we go use that to do a quantum computer? So the spins could be actually very good. So basically the idea is that we want to trap spins in quantum dots and then manipulate the state of the spins, and then the spins themselves in principle could be very good bits because they have good coherence properties. The problem is that when we trap them through this semiconductors, they lose a lot of their protection somehow. So that's the way. So now making very good operations on them is not that straightforward. The idea is that I think the day we can reach some good level of maturity on the basically how to manipulate these states, to measure these spins when they're trapped in this quantum dots, then the scaling might be much easier somehow, and making many of them would be much easier because of this all the nanofab techniques that have been developed in the semiconductor industry. But at least today, I think they are still far behind somehow, these two platforms with respect to demonstration of proof of principle requirements for this error correction to work. So yeah, I would say the platforms I mentioned are the ones really that have shown all the building blocks of an error corrected quantum computer.